Welcome to Lecture 6. This week we're going to start talking about a new type of mathematics. We're going to start talking about combinatorics, which is a fancy way of counting, and we're going to start talking about probability. First, let's talk about some basic counting principles. We start with the addition principle. Let's suppose we have two sets, A and B, and let's suppose we know the number of sets in A, the number of elements in set A, and the number of elements in set B. Then the number of elements in A union B is the number of elements in A plus the number of elements in B. But if we do that, then we're going to be counting some elements twice. The elements which are in both A and B, we would count twice. So we need to subtract the number of elements in A intersection B. So, for example, let's suppose Ali has 3 yellow shirts and 2 blue shirts. How many shirts does Ali have? Well, because a shirt is either yellow or it's blue, it can't be yellow and blue. We don't need to worry about the intersection of the set of yellow sets and the set of blue sets. So we just do 3 plus 2. In a college, there are 8 students studying mathematics, 12 students studying physics, and 5 students enrolled in a joint chemistry, physics, and mathematics program. How many students are studying either mathematics or physics in total? Now we have intersecting sets. We have the set M of the students studying mathematics and the set F of the students studying physics, and these sets overlap because some students are studying both mathematics and physics. So we use the formula. It's going to be the number of students studying mathematics plus the number of students studying physics minus the number of students studying both mathematics and physics, so that we don't count the same student twice. So using the numbers from the question, that was 8 plus 12 minus 5, the answer is 15. Next, let's move to the multiplication principle. If an operation O1 can be done in n ways, and another operation called O2 can be done in m ways, then that means there are n multiplied by m possible ways to do O1 followed by O2. So, for example, let's suppose a man has 5 different shirts, 3 different ties, and 2 different pairs of trousers. In how many different ways can this person wear a shirt, a tie, and a pair of trousers? By the multiplication principle, we just multiply these numbers together. So that's 2 trousers multiplied by 5 shirts multiplied by 3 ties. 2 multiplied by 5 multiplied by 3 gives us our answer. There's 30 different choices of outfit. Next example. 4 cities called Aberdeen, Birmingham, Coventry, and Derby are joined together by roads as shown above. How many different routes can a vehicle travel from A to D without going back on itself? So the idea is we're going to start at A, and then we're going to travel from A to D. And we can't go backwards. We're going to imagine these roads all one-way roads. So the first thing to say is there's 2 possibilities if we're going to go from A to D. We can either pass through B or we can pass through C. If the vehicle passes through B, then that means there's 4 different ways, 4 different roads to go from A to B, but then only one road which goes from B to D. We multiply these numbers together. There's 4 different routes from A to D if it goes through B. Now let's do the other possibility. Let's suppose we go from A to C and then from C to D. Between A and C, there's 2 roads, and between C and D, there's 3 roads. We multiply these 2 numbers together. There's 6 different routes from A to D. And then add these together. 4 plus 6 gives us the answer. There's 10 different routes from A to D. How many divisors does 2,800 have? A divisor is a number which will divide 2,800 and it will leave a natural number. So for example, 2 is a divisor of 2,800 because if we do 2,800 divided by 2, then we get a whole number. To answer this, I want to factorize it into prime numbers. 2,800 is 1 multiplied, and then the primes, 2 multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 5, multiplied by 5, multiplied by 7. Let's suppose we want to create a divisor of 2,800. Then we're going to use some or all of these numbers. We want to use some of the 2's. We could use 0 of the 2's, or 1 of the 2's, or 2 of the 2's, or 3 of the 2's, or 4 of the 2's. If we count 0, 1, 2, 3, 4, that means there's 5 different choices of how many 2's that we use, or 4 plus 1. Next, let's look at the 5's. There's 2 5's here. We could choose to use none of the 5's, or we could choose to use 1 of the 5's, or we could choose to use both of the 5's. We count on our fingers 0, 1, 2. That means that there are 3 different choices of how many 5's we use. And then finally, how many 7's could we choose? We could choose to have 0 7's, or we could choose to have 1 7. So there's going to be 1 plus 1 or 2 choices of how many 7's we use. And these are all independent. How many 2's we choose doesn't affect how many 5's we choose, and that doesn't affect how many 7's we choose. So there's going to be 5 multiplied by 3 multiplied by 2, or 30 different choices of numbers that we use to create a divisor. So that means there's 30 different divisors of 2,800. And in fact, I've written down these divisors. The divisors are 1, 2, 4, 5, 7, 8, 10, 14, 16, 20, 25, 28, 35, 40, 50, 56, 70, 80, 100, 112, 140, 175, 200, 280, 350, 400, 560, 700, 1,400, and 2,800. And if you count these, 1, 2, 3, etc., you will see that there are 30 divisors of 2,800. In general, the rule is this. Let's suppose that P1 up to Pn are prime numbers, and let's suppose x is P1 to the power K1 multiplied by 2P2 to the power K2, etc. Then we have a formula for the number of divisors of x. Using the same idea as on the previous slide, as K1 plus 1. The plus 1 was because we could choose to use 0 of the P1s, multiplied by K2 plus 1, etc., multiplied by Kn plus 1. Divisors of x. Now let's move on to some more advanced counting methods. We're going to be talking about permutations and combinations. But before we get that, we need something called a factorial. This is the product of the first n natural numbers. It's pronounced n factorial, and we write it as n exclamation mark. So n factorial means n multiplied by n minus 1, multiplied by n minus 2, multiplied by ... multiplied by 2, multiplied by 1. There's one more rule. We define 0 factorial to be equal to 1. And then after we've done that, we have the property that if n is 1 or bigger, n factorial is n multiplied by n minus 1 factorial. So for example, 4 factorial means 4 multiplied by 3 multiplied by 2 multiplied by 1, which is 24. 7 factorial divided by 5 factorial means 7 divided by multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 divided by 5 factorial. But 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 is just 5 factorial. So on the top, we have 7 multiplied by 6 multiplied by 5 factorial and then divided by 5 factorial. So we just end up with 7 multiplied by 6, or 42. Likewise, and I leave this one for you to check, 52 factorial divided by 5 factorial, 47 factorial is 2,598,960. Put that into your calculator and check that for me, please. Now, note that n factorial grows very rapidly. 5 factorial is 120. That's not too big, but 10 factorial is more than 3 million, and 15 factorial is more than a British billion or an American trillion. Now let's start talking about permutations. Let's imagine that we have 4 pictures and we want to hang all 4 pictures on a wall like this. How many different ways are there to arrange them? So let's suppose our 4 pictures are all of cartoon characters. Let's suppose we have Bugs Bunny, Daffy Duck, Taz, and Tweety. And let's suppose we arrange them like this, and we can count. This is arrangement number 1. Or let's suppose we swap 2 of them. We could do Bugs, Daffy, Tweety, Taz, and that's arrangement number 2. Or we could do Bugs, Taz, Daffy, Tweety, or Bugs, Taz, Tweety, Daffy, and so on. Let me say ... because I'm not going to list every possible way to arrange them. How could we calculate how many different ways there are to arrange them? Well, think of it like this. First, we should choose which picture we put in the left picture frame. We've got 4 choices. Let's choose one of these. Let's say we choose Tweety. But we had 4 different choices here. And then let's move to the second picture frame. Now we have 3 pictures left. We're going to choose one of these 3 pictures and we're going to put it in the second picture frame. So that means we have 3 choices here. After we've made that choice, we move to the next one. There's 2 pictures left. We have 2 choices for which picture to put here. Put one of them in. And then move to the last one. There's only 1 picture left, so now there's only 1 possible choice. 4 choices for the first picture frame, 3 choices for the second one, 2 for the third one, and 1 for the fourth one. Multiply these numbers together, and we find that we have 24 different ways to hang our pictures on the wall. This is called a permutation. A permutation of a set of distinct objects is an arrangement of the objects in a specific order without repetition. So like with the pictures, we have 4 different pictures. We can't repeat the same picture in 2 different frames. After we've used it, we can't use it a second time. We have a way to write the number of permutations of n distinct objects without repetition. We write that as npn. And we have a formula for this. Just like in the previous example with the 4 pictures, npn is equal to n factorial. In the previous example, n was equal to 4 because we had 4 different pictures, so 4p4 is equal to 4 factorial, or 24, as we found already. But let's make this a little bit more advanced. Now, again, let's suppose we have 4 pictures, but we don't want to hang all 4 of them. Let's suppose we only want to hang 2 of these pictures on our wall. How many ways are there to hang 2 pictures out of 4 pictures, if the order is important? Well, this time I'm going to count them. We could do Bugs and Daffy, number 1, Bugs and Taz, Bugs and Tweety. That's all of the ways to put Bugs first. Or we could do Daffy Bugs, Daffy Taz, Daffy Tweety. Or Taz Bugs, Taz Daffy, Taz Tweety. Or Tweety Bugs, Tweety Daffy, Tweety Taz. If we counted them all like this, then we can see that the answer is going to be 12. But there should be a neater way to work this out without having to write down the list of all the possibilities. Let's go back to thinking of it in the way that we did in the previous example. We have our 2 picture frames, and we need to choose first which picture we're going to hang in the left picture frame. And there's 4 different pictures that we could choose. So we have 4 choices for the left picture frame. And then we move to the right picture frame. And now there's 3 pictures left. We've already used 1, so there's 3 left. We have 3 different choices for the second picture frame. So that means 4 multiplied by 3, or 12 different choices. So there are 12 different ways to hang 2 pictures out of 4. How can we write this in terms of n factorial? Well, think of it like this. We know the answer is going to be 12, or 4 multiplied by 3, and that's the same as 4 multiplied by 3 multiplied by 2 multiplied by 1 divided by 2 multiplied by 1. So we could write this as 4 factorial divided by 2 factorial. Remember this when we come to the general formula. Let's start with the definition. A permutation of a set of n distinct objects. That's how many objects we have in total. In the previous example, n was 4. Taken r at a time. How many objects do we take? In the previous example, we took 2 of our 4 objects. So in the previous example, r was equal to 2. Without repetition is an arrangement of r of the n objects in a specific order. the number of such permutations is denoted by NPR. First, the bigger number, the number of objects that we have, and then the smaller number, the number of objects that we take. For example, let's suppose we have 3 objects, and we're going to call these objects A, B, and C. And let's suppose we're going to take R of these 3 objects. Then the possible permutations look like this. First of all, if we take only one of the 3 objects, we could choose to take A, or we could choose to take B, or we could choose to take C. So that means that 3p1, the number of permutations of 3 objects, taken one at a time, is equal to 3. Next, let's look at the second column. Let's suppose from these 3 objects we take 2 of them. What are the possibilities? We could take AB, or AC, or BA, or BC, or CA, or CB. If we count these, there's 6. 1, 2, 3, 4, 5, 6. 3p2, the number of permutations of 3 objects taken 2 at a time, is 6. And then finally look at the right-hand column. If we take all 3 of these objects, we could take ABC, or ACB, BAC, BCA, CAB, or CBA. Again, there's 6 things on this list, so 3p3 is equal to 6. Now it's time to get the formula. The number of permutations of n distinct objects taken r at a time without permutation, NPR, is n factorial divided by n minus r factorial, where r is the smaller number, n is the total number of objects we have, and r is how many we take. So I've written this formula at the top, and we're going to use it to answer this example. Find the number of permutations of 16 objects taken 3 at a time. We're asked to calculate 16p3. So we just need to put the number 16 and the number 3 into the formula. 16 factorial divided by 16 minus 3 factorial. I'll leave it for you to check that that is equal to 3,360. So that's permutations, but there's another word in the title. We also want to talk about combinations. Let's talk about the Turkish National Lottery. To enter this, you need to choose 6 numbers from a choice of 49 numbers. My question is, how many different ways are there of choosing 6 objects from a total of 49 objects? Well, the first thing to note is the answer is not 49p6. Why? Because the order of the numbers does not matter. If we're watching the draw of the lottery, 28, 69, 7, 35, 47, if that comes out of the machine, that's the same as getting 7, 9, 16, 28, 35, 47. It doesn't matter which order these balls come out of the machine. All that matters is which numbers come out of the machine. So it's not permutations if the order doesn't matter. Instead, we have something called a combination. A combination of a set of n distinct objects, taking r at a time without repetition, is an r element subset of the set of n objects. the arrangement of the elements in the subset does not matter. We're going to denote the number of combinations by NCR. So for example, let's just suppose again that we have 3 objects labeled A, B, and C, and let's suppose that we take R of these objects. And I'm going to bring up a table like before. First, let's look at the left column. How many different ways are there to take one object out of 3 if the order doesn't matter? We could take A, or we could take B, or we could take C. So there's 3 different choices. 3C1 is equal to 3. Next, let's look at the middle column. We could choose A, B, and remember that if the order doesn't matter, that's the same as BA. Or we could have AC, and because the order doesn't matter, that's the same as having CA. Or we could have BC, which is the same as having CB. There's 3 different ways that we could take 2 objects out of 3 if the order doesn't matter. So 3C2 is equal to 3. And then finally, look at the right-hand column. If we want to take all 3 of these objects, then there's only one possibility, A, B, and C, because the order doesn't matter. So ABC is the same as BAC or CAB, etc. 3C3 is equal to 1. If the order does not matter, then there's just one way to take 3 objects out of 3. Let's take the general formula. The number of combinations of n distinct objects taken r at a time without repetition, NCR, is n factorial divided by n minus r factorial, r factorial. I'm going to put this at the top of the next slide. For example, a collector has 20 different coins. How many different ways can 6 coins be selected? Because we don't care the order that we select these 6 coins, we don't use permutations, we use combinations. The question is asking us to calculate 20C6. So we put 20 and 6 into the formula, and then I'm going to leave the calculation for you to check. Check it later and tell me if there's any mistakes here. I think the answer is 38,760. Now we're ready to answer the lottery question. How many different ways are there to choose 6 numbers out of a choice of 49 numbers if the order doesn't matter? The answer is 49C6. Put the numbers 49 and 6 into the formula, and then we find that there are almost 14 million different choices, different combinations. So let me just recap. If we're using permutations, our formula is n factorial over n minus r factorial. That's if the order is important. If the order is not important, then we use combinations. NCR is n factorial divided by n minus r factorial, r factorial. For example, from a group of 9 people, in how many different ways can a chairperson, a vice chairperson, and a secretary be elected? Assuming that one person cannot hold more than one position. And then question 2, in how many ways can we choose a committee of 3 people? Okay, so first, let's suppose we're going to choose the chairperson, the vice chairperson, and the secretary. And let's suppose we have 9 people to choose from. First, let's choose the chairperson. There's 9 people that we could choose, so there's 9 different choices of chairperson. Let's choose one of the people and put them in the box. That leaves us with 8 people to choose the vice chairperson from. And then after we've chosen one of those, we need to choose the secretary. We've got 7 people left with which to choose the secretary. So that means 9 multiplied by 8 multiplied by 7, or 504 different ways to choose this committee. Or we could answer this question with permutations, because the order matters. First, we're choosing the chairperson, and then the vice chairperson, and then the secretary. So because the order matters, it's permutations. It's 9p3, 9 permute 3. By the formula, we can straight away calculate 504. Now let's answer the second question. From these 9 people, we're going to choose a committee of 3 people. And this time the order doesn't matter. We're just choosing 3 people out of 9 people. Because when the order does not matter, we use combinations. We do 9c3, which is 84. There's 84 different ways to choose a committee of 3 people out of 9 people. Now, permutations and combinations are similar in that repetition of selections is not permitted. However, as I've tried to emphasize, there's one important difference between them. In a permutation, the order is important. In a combination, the order is irrelevant. The key idea from this section is, when do we use NPR and when do we use NCR? Another example. From a standard deck of 52 cards, so that's 13 hearts, 13 clubs, 13 diamonds, and 13 spades. How many 5-card hands have 2 kings and 3 aces? Let me just explain the word hand here. When you play cards, you're given some cards and you hold them in your hand. This is called a hand of cards. So another way to ask this question would be, how many ways can 5 cards be chosen from 52 cards such that we have 2 kings and 3 aces? Question 2, how many 5-card hands have 2 clubs and 3 hearts? Question 3, how many 3-card hands have all cards from the same suit? So let's do question 1 first of all. How many 5-card hands have 2 kings and 3 aces? To answer this, we're going to need to use the multiplication principle and combinations. First, how many different ways can we get 2 kings? A deck of cards, a standard deck of cards, has 4 kings. So we're going to be choosing 2 out of 4. 4c, 2 different ways to choose 2 kings out of a total of 4. The standard deck of cards also has 4 aces, and we want 3 aces. So we're doing 4C3. We're choosing 3 of the aces from a total of 4 aces. And then we use the multiplication principle because we do 4 choose 2 multiplied by 4 choose 3. And I'll leave the calculation for you to check. The answer is 24. Now, question 2. How many 5-card hands have 2 clubs and 3 hearts? Well, the deck of cards has a total of 13 clubs, and we want 2 of them. We're going to be choosing 2 out of 13, so 13 choose 2. And a standard deck of cards also has 13 hearts, and we want 3 of these hearts. So we're going to be doing 13 choose 3. Multiply these 2 numbers together. 13 choose 2 multiplied by 13 choose 3. I'll leave this for you to check. I think we get 22,308. And then finally, how many 3-card hands will have all cards from the same suit? Now, remember, there's 13 cards in each suit. Let's talk about hearts first of all. We want to ask how many 3-card hands have all hearts. Choosing 3 out of 13, or 13 choose 3, is 286. But then there are also 286 hands which have all clubs, 286 hands which have all diamonds, and 286 hands which have all spades. Add these together, 286 plus 286 plus 286 plus 286, or 4 multiplied by 286. That gives us the answer 1,144. A bag contains 2 white balls and 3 red balls. In how many different ways can 3 balls be chosen if at least 1 ball must be white? So how can we do this? We could either have 1 white ball and 2 red balls, or we could have 2 white balls and 1 red ball. We'll count these and then we'll add them together. If I want 1 white ball and 2 red balls, there's 2 choose 1 ways to get a white ball and 3 choose 2 ways to get 2 red balls. And if I wanted 2 white balls and 1 red ball, that would be 2 choose 2 ways to get 2 white balls and 3 choose 1 ways to get 1 red ball. Add these together and we get the answer. There's 9 different ways to get 3 balls out of 5 if at least one of them must be white. Another example. You have 1 red ball, 1 blue ball, 1 green ball, and 3 orange balls. The 3 orange balls are identical. How many visually different ways are there to arrange the balls in a line? If we had 6 different colors, then this would be easy. It would just be 6p6, 6 permute 6. However, that's not the answer this time because we got 3 orange balls and they all look exactly the same. So the correct answer is going to be less than this. For example, if we label our balls RBG, O1, O2, and O3, then these 2 are going to look the same. RG, O1, O2, B, O3, and RG, O2, O3, B, O1, we're going to look exactly the same because all of the orange balls look exactly the same. But if we did 6PC, then we're going to be counting these twice. So let's think of it this way. How many different ways are there to rearrange the orange balls? That we can answer as 3p3, or 6 different ways to arrange the orange balls. That means if we calculated 6p6, then we would be counting each arrangement 6 different times. So to get the correct answer, we're going to take 6p6 and then we're going to divide it by 3p3 and get the answer 120. Let's do another example using this idea. In how many different ways can the letters of the word mathematics be arranged such that the vowels are consecutive? In other words, we want to rearrange these letters, but we want to always have the rule that the vowels are always next to each other. Now, the word mathematics has 11 letters, and 4 of these are vowels, and these 4 vowels must be consecutive or next to each other. So what we can do is we can group these 4 vowels together and think of them as a single object. So instead of thinking that we have 11 different letters, we're going to think that we have 8 different objects, M, T, H, M, T, C, S, and then all of the vowels. We're going to do this in 2 steps. First, we're going to ask how many different ways could we rearrange these 8 objects, and then we're going to ask how many different ways can we rearrange the vowels. So first, for these 8 objects, we've got 2 M's, 2 T's, 1 H, 1 C, 1 S, and 1 vowels. If these were all different, then the number of ways to arrange these 8 objects would be 8p8, but they're not all different. We've got 2 M's. So to take care of that, to make sure we're not counting the same arrangement twice, we divide by 2p2. We also have 2 T's. So that we don't count the same object twice, to take care of having 2 different T's, we also divide by 2p2. So that's 8 factorial divided by 2 factorial divided by 2 factorial, or 10,080. One more step. We need to ask how many different ways can the vowels, A, E, A, I, be arranged. We've got 2 A's, 1 E, 1 I. So that means there are 4p4, 4 objects, and then divided by 2p2, or 12 different ways to arrange the vowels. We divided by 2p2 because we've got 2 letter A's. One final step. We're going to multiply these 2 numbers together. 10,080 multiplied by 12 to get our answer. Let me say 2 things before I finish this chapter. If you have a scientific calculator, look on your calculator and see if you can find the NPR and NCR options. Or perhaps the best online calculator is Wolfram Alpha, either a website or a smartphone app. You can try typing 7 permute 3 or 7 choose 3 into Wolfram Alpha to get your answers. Now I'm going to take a 10-minute break before I start talking about probability. And now let's continue. Let's start talking about probability. We'll do the introduction this week, and then next week we'll do the main theory of probability. To start with, let's suppose we're going to roll a single standard six-sided die. What are the possible outcomes? What number could appear on the top of the die? We could get a 1, a 2, a 3, a 4, a 5, or a 6. If we put all of these outcomes in a set, then this set is called a sample space. Each of the numbers in S is called a simple event. So in this picture, the number 6 appeared on the top of the die. 6 is a simple event. Now let's suppose that we're interested in rolling an even number. So we want either a 2 or a 4 or a 6. This gives us a subset of the sample space. This subset is called a compound event. Well, generally, if we have a set containing E1 up to En, this is called a sample space if two rules are satisfied. First of all, if S contains all of the possible outcomes of some experiment, and rule number 2, one and only one of the outcomes in S must occur. An event, E, is any subset of S. And when we say any subset, we include the empty set, that's the circle with a line through, and we include the whole set S itself. Each one of the EIs is a simple event. If we have capital E is the set containing EI, that's also called a simple event. But if E is a subset which contains more than one element, then it's called a compound event. Now let's suppose we're going to be rolling 2 dice. What are the possible outcomes of rolling 2 dice? Well, from the first die, we can get 1, 2, 3, 4, 5, and 6. And from the second die, we can also get 1, 2, 3, 4, 5, and 6. So, for example, we can get a 2 and then a 3, or a 3 and then a 2, or a 4 and a 4, etc. We can see from this table that there are 36 different outcomes of rolling the 2 dice. If we're rolling 2 dice, then the sample space is the set containing all of the pairs A and B, where each of A and B is a number between 1 and 6. My question is, what is the event which corresponds to a total score of 7, a total score of 3, a total score greater than 10, a total score of 2? First question, what is the event which corresponds to a total score of 7? How could we get 7 in total? We could have 1 and 6, or 2 and 5, or 3 and 4, 4 and 3, 5 and 2, or 6 and 1. We have a subset containing 6 elements. This is a compound event. How could we get a total score of 3? We could have 1 and 2, or 2 and 1. Another compound event. How could we get a total score which is greater than 10? Scores greater than 10, that means either 11 or 12. To get 11, 5 and 6, or 6 and 5. To get 12, 6 and 6. And then finally, how could we get a total score of 2? There's only one way we can get a total score of 2. We'd have to roll 1 on both dice. This event contains only one object, so this is a simple event. Let S be a sample space containing n simple elements. The probability of event EI is a real number which we call P of EI, and this must satisfy two rules. Rule number one, the probability of event EI must be a number between 0 and 1. And rule number two, if we add up all of the probabilities of the simple events, then we must get 1. For example, let's suppose we're flipping a single coin. Then the sample space is either we have heads or we have tails. And we can assume that we have a fair coin. We can assume it's equally likely that we get heads or we get tails. So we can assume that the probability of heads is a half and the probability of tails is a half. Now note this satisfies both rules. Rule number one, both probabilities need to be between 0 and 1. Yes, we have that. And rule number two, if we add the probabilities of the simple events together, a half plus a half, we must get a total of 1. And let me just finish by remarking that if we flip this fair coin 1,000 times, we would expect to get H roughly, not exactly, but roughly 500 times. The probability of an event capital E must satisfy the following rules. The probability of the empty set must be 0. The probability of the whole sample space S must be equal to 1. If capital E is a simple event, that's a subset which contains only one element, then the probability of capital E must be the same as the probability of EI. And rule number 4, if capital E is a compound event, that's a subset which contains more than one element, then the probability of E must be equal to the sum of the probabilities of all the simple events in E. So, for example, if capital E is the compound event containing 3 objects, let's call them A, B, and C, then the probability of capital E must be the probability of A plus the probability of B plus the probability of C. Now, let me just remark, if we see probability of an event is equal to 1, that means E is certain to occur. If we see that the probability of E is equal to 0, that means that E will never occur. 0 probability means it does not occur. Probability of 1 means it's certain to occur. It will always occur. Now let's suppose we've got 2 coins. Let's suppose we're flipping 2 different coins. First of all, what is the sample space? Well, we could get heads and heads, or heads and tails, tails and heads, or we can get tails and tails. And we're going to assume that these 2 coins are fair coins. So we're going to assume that on each coin it's equally likely that we get a heads or we get a tail. So the probability of each of these simple events is going to be a quarter. Question 1, what is the probability of getting 1 head and 1 tail? Question 2, what is the probability of getting at least 1 tail? Question 3, what is the probability of getting at least 1 head or at least 1 tail? Question 4, what is the probability of getting 2 tails? Question 5, what is the probability of getting 3 tails? Question 1 then, what is the probability of getting 1 head and 1 tail? How can we get at 1 head and 1 tail? We could have a head and a tail, or we could have a tail and a head. So our compound event contains two simple events, two objects. And then the probability of E is going to be the probability of heads tails plus the probability of tails heads. So it's a quarter plus a quarter, which is a half. Question 2. What is the probability of getting at least one tail? So let's make a list of the ways that we can get at least one tail. We could have heads and tails and heads, or we could get tails and tails. So the probability that we want is the probability of heads tails plus the probability of tails heads plus the probability of tails tails. So 3/4. Question 3 was, what is the probability of getting at least one head or at least one tail? We'll make a list of the ways we can get at least one head, 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 tail, tail, head, and the ways that we can get at least one tail, heads, tails, tails, heads, and tails, tails has at least one tails. But that's all of the sample space S, and the probability of the sample space S is always equal to 1. What is the probability of getting two tails? Now we have a simple event because the only way of getting two tails is by giving tails tails. So the probability of E here is a quarter. And then question 5 was, what is the probability of getting 3 tails? It's not possible to get 3 tails if we only have 2 coins. So our event E is going to be the empty set. And the probability of the empty set is always 0. It's not possible to get 3 tails. Theorem. If we assume that each simple event in S is equally likely, then the probability of an event E is the number of elements in E divided by the number of elements in S. The next example is going to use this idea. We're going to count the number of elements in E, we're going to count the number of elements in S, and then we're going to do NE divided by NS. Let's go back to talking about 2 dice. Let's suppose we roll 2 dice, and then we're going to suppose that each simple event is equally likely. Find the probabilities of the following. And these are the same ones we talked about earlier when we talked about writing the events for each of these. A total score of 7, a total score of 3, a total score greater than 10, or a total score of 2. So remember, the way to get a total score of 7 was this compound event. This compound event contains 6 objects, and the sample space contained 36 objects. So the probability of getting a total score of 7 is going to be 6 divided by 36. Question 2. What is the probability of getting a total score of 3? Our event contains 2 objects, so we're going to do 2 divided by 36. How can we get a total score bigger than 10, greater than 10? The event that we wrote down earlier contained 3 objects, so now the probability is 3 divided by 36. And question 4, how can we get a total score of 2? This is a simple event because it contains only 1 object. We do 1 divided by 36. And then one more example, final example of today's lesson. You randomly draw 5 cards from a standard deck of 52 cards. What is the probability of getting 2 clubs and 3 hearts? So first of all, how many elements are in the sample space? How many different ways are there of choosing 5 cards out of 52? 52 choose 5 different ways. And then for our event, how many elements are in our event? We want 2 clubs out of a total of 13 clubs. So 13 choose 2 different ways of getting 2 clubs. And we want 3 hearts out of a total of 13 hearts. So that means there's 13 choose 3 different ways to get 3 hearts. Multiply these two things together. 13 choose 2 multiplied by 13 choose 3. This is the number of 5 card hands which have 2 clubs and 3 hearts. So the answer to this question is going to be the number of elements in our event, 13 choose 2 multiplied by 13 choose 3, divided by the number of objects in our sample space, so divided by 52 choose 5. And when we put this into our calculator, we found that the probability is approximately 0.0062. And that is the end of this week's lesson. Next week, we will continue talking about probability. We'll talk about concepts of probability, conditional probability, and probability trees. Are there any questions?